As the sun drops below the horizon at a high-altitude observatory, heavy steel gears engage. A massive protective shell slides open, exposing hypersensitive instruments to the freezing night sky. Engineers design these structures to serve as precision bridges, balancing the stability of the terrestrial ground with the requirements of the celestial void. The first observatories were the landscape itself. Ancient civilizations aligned massive stones and earthen mounds to the horizon, creating permanent sightlines to track the rhythmic cycles of the sun and moon. To move from simply watching the sky to accurately calculating the positions of the stars, early astronomers relied on handheld tools like the astrolabe. These instruments allowed for the first precise mapping of the heavens. By the late 19th century, the mechanics of astronomy required immense physical space. To house increasingly massive glass lenses, architects built imposing structures with high stone columns and soaring domes, like the Yerkes Observatory. But the thick atmosphere at sea level distorts incoming light. To escape the dense air, the architectural footprint eventually migrated to remote mountain peaks that sit entirely above the cloud layer. This progression from stone circles to mechanized mountaintop domes represents an escalating drive to pinpoint our exact coordinates in the universe. At these altitudes, the primary enemy of the observer is invisible. It is the residual heat from the daytime sun, trapped inside the concrete and steel of the building. This creates dome seeing. Because heat rises, the warmth absorbed by the structure during the day acts like a chimney, where warm air vents out of the dome slit and hits the freezing mountain air. This triggers Snell's law, where light bends moving between different temperatures. As starlight hits this turbulent air, it fractures and bends erratically. Instead of capturing a sharp data point, the sensor records a dancing, twinkling blur that obscures the fine details of the stars. The building must achieve thermal equilibrium to function. This requires low thermal mass materials and active ventilation to ensure the air inside the chamber perfectly matches the temperature of the air outside. To capture light from the deepest edges of space, the observatory must essentially erase its own physical and thermal presence. Beyond the building's thermal state, the astronomers themselves must physically adapt to the mountain's nocturnal environment. Navigating the dark requires the production of rhodopsin. Rhodopsin is a light-sensitive chemical in the eye's rod cells that enables vision in extreme low-light conditions. This chemical takes 40 minutes to fully form, but it is incredibly fragile. A single exposure to bright white light causes rhodopsin to instantly decay, resetting the observer's night vision to zero. To protect this adaptation, observatories enforce strict protocols. Astronomers use dim red screens and red flashlights for navigation, as red light preserves rhodopsin. The shift is a total sensory immersion. Observers eat their 3 a.m. night lunch in a red-lit control room, accompanied by the constant low-frequency hum of stepper motors, turning the telescope to counter the Earth's rotation. The human body and the mechanical dome enter a shared nocturnal rhythm, a requirement for anyone hoping to work with ancient light. These long vigils in the cold eventually provided the data that redefined the universe. In the mid-20th century, that work centered on the massive steel framework of the Hale telescope. In 1923, Edwin Hubble sat alone in the freezing observer's cage of the Mount Wilson telescope. He spent hours exposing a glass photographic plate to the faint light of the Andromeda Nebula. His discovery relied on the work of Henrietta Swan Leavitt. Leavitt had identified a way to calculate deep space distances by measuring the pulsing rhythm of stars known as Cepheid variables. When Hubble examined his plate, he found one of these pulsing stars. He crossed out the letter N for nova and scratched VARS into the emulsion, realizing he had found a variable star. The math was undeniable. Andromeda was not a local cloud within our galaxy. It was an entirely separate system, located millions of light-years away. As Hubble tracked more of these distant systems, he noticed their light was experiencing redshift. Redshift is a phenomenon where light from an object moving away from an observer is stretched, making it appear more red. This proved that all these galaxies were rushing away from us, and that the universe itself was expanding. The modern observatory functions as a quiet outpost, a place where we manage the heat of our own planet and wait in the darkness to read the history of the stars.